Hello, Richard Swiderski here again. This is the second part in my series on modifying my Kolb KXP1 Firestar to have full length uh, flaperons that will change the airfoil of the entire wing. Kind of left off around this push-pull tube operating this coming from the joystick. I could keep that tube pretty much the way it was. I had to change the length a little bit, but it just moves. It slides back and forth. The top moves back and forth as I move this slide back and forth, and it still works. Everything seemed to geometric. All the geometries worked out. It still works. The only disadvantage is that as this assembly is slid back to which would be the neutral position, the normal flying position, the joystick becomes cocked, clocked over to the side. Let's see, to my left. So you'd be flying around like you're flying in level flight, as if you're making a turn to the left. So I had to increase the length of my of this push-pull tube to bring that stick back to vertical position in normal flight. However, now when you slide the mechanism forward, the stick is clocked to the left again in straight and level flight. So I fiddle around with adjustments, and I got it to where it's straight up and down in normal flight and only slightly cocked to an acceptable level to the left in level flight with the flaperons fully deployed. One caveat before I forget, I'm not an engineer. I've been building things since I was 6. I'm 72. So I have a good feel for what's right, what'll work, and what won't. But I am not a certified engineer. So I erred in to overbuild rather than underbuild. This is heavier than what it could be. And if I was a smart engineer, I could make it probably for half the weight. As it is now, with this whole assembly is almost 5 pounds. And then when you add the telex cable and the control handle that moves this back and forth, you're going to be up to 8 pounds probably, maybe 9 pounds. Okay, so oh yes, also very important. This the early model, the Ultra Stars, and the early model Kolb Firestars came with a 0.28 wall thickness for their trailing edge spar and the leading edge spar of the aileron tube. So you can't deploy these flaps at high speed. It would, I think it would break. because the wall thicknesses are so thin. You would over torque them. You would put too much torque on the tubes. So speed management is critical. I would not want to deploy these. I haven't flown them yet, but I'm fairly confident that I would not want to deploy these in full flaps fast, any 45 mile an hour or slower. Partial deflection obviously is not a problem at all, and but I mean, when I'm talking about 45 degrees of deflection, I am pretty certain it would overstress something. Okay. The biggest problem that I had with this is if you got 40 or 45 degrees of deflection, which I can go 45 if I want to on this, although I think I'm going to settle in at 40. But if you got 45 or 40 degrees of deflection and you're going straight and level, and then you want to make it, you want to say, let's turn to the left. Now your flaperon on the left wing is going to come down, and it's going to approach virtually 90 degrees at full left turn, at full deflection for left turn. And that obviously is not a good thing. So what the heck do you do to get around that? Well, I built in differential aileron movement on this system. This tube here, I kept all the geometry as much as possible the same. All the throws are the same from the bell crank to the this push tube here, and here to here. Excuse me, I'm sorry about the camera. From here to here, from here to here, and this from here to here is all the same. But what's different is this part of the bell crank that the aileron tubes, push-pull tubes connect to, was all the way over here, about 1 inch forward of this pivot point, which in theory would give it a little bit of a differential effect, although I couldn't tell, and it was certainly insignificant. But I can't go, it would be several videos of me, I'm so verbose, I could not explain succinctly why it works, but I'll just tell you that by moving this out 4 inches, I greatly change the geometry of how the ailerons are deflected. I got a 6-to-1 ratio on paper at this with those at 4 inches and 6 inches across from this point to this point, 4 inches from the center of this tube to the center of the pivot. Okay, so I've not clocked it exactly to see if I ended up with 6-to-1. I don't think so, because if you make a model of it, the 6-to-1, it's not a linear. When you first initiate the movement, it's virtually 1-to-1 under small movements, and it only becomes 6-to-1 at the most exaggerated movements, from which you're not going to see. So I don't think I'm going to probably end up with 3-to-1 or 4-to-1 in reality. So what does that mean? That means for every 1 degree in my left turn, that the left wing aileron will deflect down, the right wing will deflect up. If it's 1 to 4, let's say, it would be 4 degrees up and 1 degree down. So now when you got your ailerons all the way deployed and you've got that steep angle on your wing, when you go to a full left turn, that down aileron is now going to it won't hit 90, it'll only going to move 1 degree for every 4 degrees up on the other wing. All right, so you're going to maintain some maneuverability, albeit it's going to be still an enormous amount of adverse yaw. You're not going to use full 45 degrees or 40 degree deflection of flaps unless you're already on final, your airspeed is down, and you're going pretty much straight ahead. You will not be able to do steep turns with full deflection. There's too much adverse yaw. I've not tried it. As I say, I've not flown it yet, but I know on the Ultrastar, it didn't like steep turns at all when it was fully deflected. When the flaps were fully retracted. Okay, I think that covers that. I better stop. I may have gone too far. Sorry. I might have to do this all over. We'll see. Bye for now.